For many years, the existence of several mass extinctions has been agreed upon in the scientific community. There has been conclusive evidence in supporting this and many reasons why they have occurred. Leading causes, however, is a less ironed-out subject that continues to be studied to this day. There have been 5 mass extinction events that have swept the world, each extinction yielding different percentages for amount of species and genera lost. If we can determine important factors and causes of past extinctions, this may help to prevent any future large loss of life. The first mass extinction was the ordovician Silurian extinction, which occurred approximately 450 to 444 million years ago. At this time, much of the world was underwater and there were only a few land masses present. The leading factor for this extinction is mainly the glaciation that occurred at the time because the large amount of marine life froze inside the water that surrounded them. This extinction wiped out 49 to 60% of marine genera and nearly 85% of marine species. The second mass extinction was the late Devonian extinction, and this occurred 420 to 360 million years ago. The Earth was mostly underwater during this time as well, and global biodiversity was on a steady decline. The main cause of this extinction were intermittent pulses of oxygen levels dropping in the ocean. Around 50% of genera and 70 to 80% of all species were lost due to this extinction. The third mass extinction occurred about 248 million years ago. This was the end-permian mass extinction, which was caused by an enormous increase of carbon dioxide into the air. There was a 96% loss of species and 50% loss of genera, causing this to be the largest mass extinction to date, which is why it's commonly known as the Great Dying. The fourth mass extinction occurred 201 million years ago. The Triassic mass extinction had a 27% loss of genera and 80% loss of species. And while causes are still disputed, it is widely believed that carbon dioxide was introduced to the atmosphere, causing global warming and changes to the ocean similar to that of the late Devonian, though on a much smaller scale. The fifth and most recent mass extinction occurred 65 million years ago, and this was the Cretaceous extinction, which was led by drastic climate and sea level changes. This extinction rendered about 40% of genera and 76% of species extinct. This extinction is generally hypothesized to have been caused by the Chicxulub impact, but this can still be and is refuted to this day. To move forward scientifically in this field of study, the National Science Foundation is hosting a conference in Austin, Texas at the Liberal Arts and Science Academy, where a grant will be awarded to the team that presents the clearest data arguing that their theory holds the most direct causation for mass extinctions across history. The teams are composed of research scientists who are either in favor of impact theory or volcanism. The impact theory side is led by Drs. Thea Dandapani and Frankie Gelati, while the volcanism side is led by Drs. Jake Matz and Leo Klein. The National Science Foundation has brought in experts on this topic to serve as committee members for this debate. These members include Drs. Evelyn Rees-Eisler, Lorelei Myint, and Charlotte Barnes. In the days leading up to the debate, all those involved are working hard to ensure that the scientific propriety of their roles in the matter, as well as the debate itself, be preserved. Here we have Dr. Jake Matz, the principal investigator of the volcanism group the day before the debate. How secure do you feel in your preparations for the debate tomorrow?
Very secure.
Can you elaborate on that?
I went through everyone's presentations today and it looks good, and I feel confident that we'll be able to shatter the impact side.
What do you think is the strongest point for volcanism?
Probably the entire Permian extinction. It was a 96% loss of species biodiversity, and it is most strongly correlated with volcanism.
What do you think about the Chicxulub crater's evidence supporting impact theory, and how will you combat this?
It's probably the biggest impact theory piece of evidence, but we're working on minimizing it because its effect on biodiversity was kind of minimal compared to some of our extinction events.
Are there any pieces of evidence you are worried about opposing?
Big thing is ocean acidification, foraminifera populations, etc., because if they could argue that that's an impact event and not volcanism, we lose about 2 extinction events.
How strongly will your side's case for eruption intervals matching extinctions on the timeline be, or in other words, how dependent are you on this factor?
We have a couple graphs set up that have all of the intervals lined up with the extinction events, so we're kind of leaning on that right now.
Do you think more recent extinctions have been affected differently by these volcanic eruptions, and what differences might they be?
Not much of a difference. It's been a consistent interval of global warming, climate change, species extinction, direct impact of the volcanic eruptions. It's about the same for all of our events.
Are there any questions you think you won't be able to answer tomorrow, specifically surrounding but not limited to sulfur and carbon cycles or glaciation?
We have a full presentation on glaciation and carbon cycles, so we should be able to sort all that out.
What are some holes you expect to find in the impact side's argument, or how do you think the debate will go in general tomorrow?
Cretaceous impact has a presentation on black soot in the atmosphere, and we're going to argue that that was actually the V-loop traps and not just the impact from their meteor. And besides that, hopefully it'll go alright. We're going first, which I was hoping for because I cite some of my questions in our presentations.
Order in the court. Okay, the guiding question is volcanism or impact the main cause, the main factor for ancient mass extinctions? So we're going to have the volcanism lab presentations, questioning by the impact PIs, and then questioning by us first. So our main rules: no talking in the gallery, no verbal communication between the gallery and PIs. Communication via internet chat is allowed. PIs cannot talk or gesture to their own research scientists while they are presenting or being questioned. PIs may not introduce info beyond their questioning. PIs may not badger scientists. PIs must allow scientists to answer the questions they have been asked. PIs can only object during the opposing investigator's questioning. There are two main reasons for objections. One, the scientist is being badgered by the opposing PIs, or two, the opposing PIs are introducing information beyond their questioning, and we will say sustained or overruled to your objection. Yeah. So the first speaker is Tianmai for volcanism.
Nope. First speaker is
Jake. Oh. Okay, first we'll have the opening statement by Jake.
Esteemed delegates, we stand here before you today not to disprove the prevalence of impacts in our great extinction events, but to prove that volcanism is the superior, more grand, and is many times over the greater factor in these extinction events, by many, many times. It's a simple fact that volcanism is an internal function, and impact theory is by random chance and external influence, and as such it cannot be accounted for every single extinction event. While you have iridium sources and charged crystal for your evidence, we have volcanic ash, rock, and layers of black shale and instantaneous loss of species to account for the devastation that volcanism brings. The Permian extinction, the Devonian, Triassic, Cretaceous, and Ordovician, our scientists have spent the past week studying all of them to get concrete evidence to prove our stance. And we stand here before the delegates today to strive for the grant for volcanism in our coming research.
Esteemed delegates, I am here today with my lab, the Impact Lab, and we are competing for the NSF Career Grant of $500,000. With this grant, we can help improve and further research impact and its impact on mass extinctions, and we can come to concrete conclusions on what has happened in the past. The main prompt for this debate was what was the most important physical factor that has led to mass extinctions in the past. There are two options: impact, which is extraterrestrial objects hitting the Earth, not aliens, and volcanism, which is massive volcanoes. Main pieces of evidence for impact, which is the clear right answer, are the Cretaceous mass extinction, Devonian mass extinction, and the Triassic-jurassic mass extinction. The Cretaceous extinction presents concrete evidence impact through the KT boundary, the Chicxulub crater, the rock strata in Gibbio, Italy, and Foraminifera. The Devonian mass extinction also has this evidence with the Siljan impact structure, the Flynn crater in Tennessee, the Alamo Bolidae, I don't know how to pronounce that one, impact, and this leads to suggestions of many smaller but they're still big impacts. In the Triassic extinction, there's a claystone layer found in Japan that is very evident of extinction, with fossils being only found below it, and a Manicouagan crater in Canada also found that was dated to be around the same time. There's even evidence for impact in the Permian extinction. Zhu Daoyi proposed an impact from a stony meteorite because of the low iridium abundances. Shocked quartz was found on the PT boundary in Australia as well. The most convincing piece of evidence are the trapped gases in China and Japan, which are similar to those in the KT boundary. With this, we can conclude that evidence for impact outnumbers volcanism in both quality and quantity, and almost every extinction has some evidence of impact. We'd like to thank you guys for listening today, and we are excited to see the results of this debate.
The debate begins with the Volcanism Lab, and Ms. Tanmai Nguyen is the first to speak. In her presentation, she discounts impact evidence for the Permian-Triassic mass extinction. She began by stating that the crater in Australia that had been used as backing evidence for impact in the end-Permian should be discounted because of the lack of iridium found at the site. Iridium is a dense chemical that is rarely seen on Earth. It is more commonly seen in meteorites than in the Earth's crust, which is why most impact scientists use it as a key point of evidence when arguing their case. It is also why Tanmai is able to conclude that due to a lack of iridium, impact in the end-Permian was unlikely. Tanmai also mentioned shocked quartz, which is a form of quartz that has undergone an immense amount of pressure, which results in the crystalline structure being deformed along planes inside the crystal. This is another driving piece of evidence for the impact side, more specifically against volcanism, because a volcanic eruption could not generate the required pressure to cause this effect. Tanmai, however, states that the shocked quartz samples at the Permian-Triassic boundary are minuscule and ambiguous, and overall are seen as weak evidence. Tanmai then begins to present how helium isotopic ratios provide evidence for how impact was not present in the end-Permian extinction. She states that the most common isotope of helium is helium-4, and that a spike in helium-3 to helium-4 ratio would be evidence for an extraterrestrial object hitting the Earth. She references many scientists who gathered samples of volcanic ash along the Permian-Triassic boundary to test for a spike in helium-3, which there wasn't. This indicates little to no involvement of any extraterrestrial impact. During the questioning period, Tanmai's overall argument is that even if impact had any involvement in the end-Permian extinction, its performance was of little to no consequence in the causation of the extinction. Next up is Mr. Anshul Desai, who is presenting how and why Siberian volcanism is the leading factor for the end-Permian extinction. Anshul states that large igneous provinces present in Siberia are believed to have a large role in the end-Permian extinction because air and sea temperatures began rising after the Siberian volcanoes erupted, and they released a large amount of greenhouse gases into the atmosphere in a really short period of time. He then goes on to explain delta C13, which is a huge indicator for volcanic involvement. Delta C13 is a measure of the ratio between stable isotopes carbon-13 to carbon-12. This is significant because plants take in carbon, and when they die, C12 in the atmosphere will increase, causing the C13 to C12 ratio to decrease. Anshul then begins to present using this graph to provide further evidence supporting the effects of volcanism at the time. While there's a lot going on, he's mainly focused on the presence of this studied plant and the introduction of this charcoal, specifically how the plant is abundant near the Permian-Triassic boundary and stops existing at the same time at which the charcoal is introduced, which indicates major volcanic involvement. During the questioning period, Anshul's overall argument is that there is just so much evidence indicating volcanism that has little to no possibility of being tied to impact. Next is Mr. Alex Mims, who's presenting Anoxia, euxinia, and volcanism in the late Devonian. He starts by describing what the world was like during the Devonian period, which was essentially mostly underwater, so marine life was most prominent during this period. He also states that volcanoes were known to be active at this time, listing the Veluwe traps in Siberia as an example, and we know the age of these volcanic rocks through potassium-argon dating. The way that this works is the potassium crystals that form in magma are still present in the igneous rock when the magma cools, and there's a specific isotope of potassium, potassium-40, and over time it radioactively decays and becomes argon-40. And potassium-40 has a half-life of 1.3 billion years, so we're able to determine the age of the volcanic rock by comparing the amount of argon-40 to the amount of potassium-40 that's left. Using this method, it can be found that the Veluwe traps contain igneous rock that dates back to the late Devonian period. Alex relates volcanic effects to the late Devonian mass extinction through ocean anoxia and euxinia. He explains that ocean anoxia is when the ocean is depleted of dissolved oxygen, and this is most common at the bottom of the sea. He also explains what euxinia is, which is when anoxic water becomes sulfidic and overall becomes acidic and lethal to marine life. This all comes together when he states that black shale found in Vietnam dating back to the Devonian period was found to have minerals in it that directly relate to ocean anoxia and euxinia, which proves that these minerals were released by volcanoes and had been the leading cause in the late Devonian extinction. During the questioning period, Alex's overall argument is that the mercury and other mineral presence is clear evidence pointing towards volcanism being the main cause of the late Devonian mass extinction. Next up is Mr. Abinu Mecca, who is presenting on Deccan Volcanism as a major player in the Cretaceous extinction. Before speaking about the effects of volcanism during this period, Abinu begins refuting the idea that the Chicxulub impact caused the Cretaceous mass extinction by stating that the proof of impact lies too far below the KT boundary and therefore predates the extinction. He also states that microtectites and variants were not present after the KT boundary, which he uses as further evidence supporting the idea that the Chicxulub impact predates the Cretaceous mass extinction. He then begins explaining how the Deccan traps, which are located in western India and were one of the world's largest lava flows, are the main cause of the extinction. He explains that there were 3 pulses to this, and the second one was so strong that it accounted for 80% of the lava flow, and that it directly precedes the KT boundary. Abinu explains that this lava flow was the cause of the extinction by stating that sulfate was among the gases released into the atmosphere, and it reflected any sunlight back into space, preventing any from reaching the Earth. During the questioning period, Abinu's overall argument is that because the Chicxulub impact predated the Cretaceous mass extinction by a large amount, it had no effect on the extinction whatsoever. Next, we have Mr. Milan Mutala, who is presenting why camp volcanism is the leading cause for the triassic-jurassic extinction. He explains that there was a sharp change in the radiolarian fauna and conodonts right above a layer of tuff, which all dates back to around 200 million years ago. He also uses the ratio between argon-40 and argon-39 as evidence for camp because it suggests a peak in volcanic activity around 200 million years ago, as well as delta C13, which was previously mentioned. Milland also brings up another use for examining delta C13, which is looking at why C12 increased along with global warming. He explains that this was likely caused by the release of methane through the dissociation of gas hydrates, which are only stable in a certain range of low temperatures. Using this evidence, Milland states that camp volcanism was responsible for the Triassic-Jurassic extinction, more specifically the marine life. This is also supported by the strontium isotopic ratio of SR87 to SR86, where SR86 is caused by submarine volcanism. Here's footage of Mr. Mutala's questioning period, in which his overall argument can be referenced as in opposition to Mr. Connor Magali's supporting impact for the same extinction. Mr. Magali is to be interviewed after the presentations conclude, and the questioning periods for both can be used as context for the interview.
Volcanic activity usually results in the release of certain elements, right? And differences in the isotopic abundances of certain things. So based on this and what I read in the article, I think that this would be a more probable cause of more nutrients in the ecosystem. But I guess impact could also have a slight probability to cause this, but I don't really research how the impact affected this.
Do you know how long camp was erupting in comparison to the time span of the Triassic-Jurassic extinction?
Yeah, so basically, there's like 2 sides to it. So it's like split. So sometimes it thinks that it was like a short, intense period of volcanic eruptions and magma, while some believe that it was like continuous eruptions. But either way, the time linked up between like 199.6 or 199 to like around 201 million years ago, the volcanic activity, which also coincides with the Triassic-Jurassic boundary.
Yes, but if it was continuous eruptions over a longer span of time, then would it have gone on longer than the period itself of Triassic-Jurassic, or would it have stopped before?
Well, it wasn't really like that continuous. I would say, I guess that was my mistake. It was more like short periods, but happening more often than once. And either way, the tough layer only signifies this to happen around 199.6 million years ago, but other scientists haven't provided research, or at least in my article, that it extended past the Triassic period, or the end Triassic period. So based on the articles I read, I didn't see any mention of it extending past the period, but it may have. But I guess I didn't see any evidence of that.
It's time.
Okay. So you mentioned a sharp change in the stuff above the tuff. I didn't quite catch that. Could you?
Yeah. So basically, the radiolarian fauna, as I mentioned, and conodonts, which were popular species or abundant species during this time, there was a sharp change or drop in their abundance, and like you can see a lot of their fossils right above a tuff layer, and the tuff, as we know, is resulting from volcanic eruptions, and that layer was dated to be around, as I said, 199.6 million years ago.
Okay. And could you explain how volcanic activity leads to enhanced nutrient delivery?
I'm not exactly sure about this as I read in my article, but as they mentioned, it was just that when the volcanoes erupted, there was more carbon released into the atmosphere, along with methane and other elements. The composition of other elements also changed in the environment, and so these changes in these elements may have caused extra nutrients to be deposited in the oceans, or extra nutrients to be available in the oceans.
And this is just an opinion question. So this Triassic extinction was a result of global warming and climate effects. What reflections can be made relating to current times with what would happen if a volcanic activity would happen today?
Well, I mean, I think there aren't, as I said, the camp was very widespread and large. I don't believe we have that large of a volcano in the present day, or at least, and I think if it were to happen, I don't think it would have as much of a significance because of the size, but I think it would definitely affect the same number of or not the same number, it would affect marine and terrestrial environments through, as I said, eutrophication and changes in carbon and methane released. So I think it would still be affecting places worldwide because of global warming, but I think it might not be as much, but it will still have a significant effect.
Next up is Mr. Adrian Woodruff, who is presenting the effects of camp volcanism in the terminal Triassic. He begins by stating the underlying cause of the Triassic mass extinction, the major basalt flood eruption from the Central Atlantic Magmatic province. Up next is Mr. Carter Sherrill, who is presenting evidence for volcanism in the late Ordovician, where and how. Here is footage of Mr. Sherrill's questioning period in which his overall argument can be referenced. Mr. Sherrill is to be interviewed after the presentations conclude, and the questioning periods for both him and his counterpart, Miss Fleming, can be used as context for the interview.
So, another scientist will be talking about that, but I can talk about that a little bit. So, there are certain gases that the volcanoes release, such as sulfur dioxide, like Hayden talked about a little bit. And that sulfur dioxide can turn into sulfur aerosols, and I think somebody mentioned it before, it will reflect the UV rays of the sun, which will dramatically cool the earth, and there's also lots of ash from volcanism, and it's mainly the fine particles, and those that from very large eruptions can encompass the whole entire earth in the very upper atmosphere, and that can also block lots of sunlight, which causes rapid cooling in a very short amount of time.
Is that uniform for all volcanic eruptions?
So mainly what happens is you have cooling, and then you have heating afterwards, after lots of the ash and those sulfur aerosols are absorbed into the earth. So first you have cooling, and then you have the global warming. And that's what we can see with the Eurasian glacial expansion. You can see a rapid expansion of the glacier and then a rapid contraction, which causes the 2 points in the end of Ordovician extinction. If you look at the extinction marker,
I don't know if it shows it on here, but there's like two little dips. You have like a first dip and then a second one right after. And that's what is the expansion and the contraction of the glacier.
Do we see this present in other mass extinctions thought to be caused by volcanism?
I did not research that.
It is time.
This is more of an opinion question, but why do you think there was so much volcanic activity during this time? Do you know anything about the movement of tectonic plates?
I did not study that.
That concludes day 1 of the NSF conference, and the same people joined together the next day, November 15th, to continue the debate. First to present today is Lillian Holland, who will be continuing the topic of volcanism during the ordovician extinction, specifically surrounding how volcanism caused the glaciation at this time. During the questioning period, Lillian's overall argument is that though impact may have had the same effects on the environment, there is more evidence present to suggest volcanic interference. Then, to begin presentations for the impact side is Mr. Nathan Chu, who is going to talk about how an asteroid impact ended the Cretaceous, specifically how the impact caused climate change at this time. During the questioning period, Nathan's overall argument is that a volcano could not have been capable of forming that much soot due to a lack of energy, especially compared to the possibilities of the Chicxulub impact. Next is Mr. Connor Magali, who is presenting evidence from the fossil record during the Triassic extinction. He begins by explaining that there were 5 main sites of impact in the northern hemisphere: SM, RW, M, SW, and R during the late Triassic. M and SM are in modern-day Canada, R is in France, P is in Finland, RW is the US. Connor explains that ammonoids and conodonts are the most abundant fossils found at these sites, and after impact there were no fossils of the sort present. Here is footage of Mr. Magali's questioning period, in which his overall argument can be referenced. Mr. Magali is to be interviewed after the presentations conclude, and the questioning periods for both him and his counterpart, Mr. Matala, can be used as context for the interview.
I'm not very knowledgeable of the volcanism, but I believe that the proximity of these fossils in this area and like the evidence of, yes, the proximity of the fossils to and around these areas make me believe that it was caused by impact.
Okay.
How close are these fossils to the meteorite impact?
Some of them are actually in it, and others are actually within like a couple mile radius. I don't know the exact distance.
I don't mean proximity of them physically, I mean time-wise.
Oh, time-wise? When they went extinct, like right on it, the impact caused their extinction. They died off anywhere around the area.
Do you have evidence for this?
I read it in one of the articles that this happened, yes.
Did you cite any of it in your presentation?
Sustained.
No further questions?
So you said the proximity of the fossils proved that it was the impact, right?
Yeah.
So did these impacts not affect the world on a global scale?
I'd say there's definitely are factors from the meteor impacts that affect the whole world. I just didn't focus in on those. I just focused in on the close proximity and the impacts affecting the ammonoids and conodonts in these specific areas.
Do you know what methods or how accurate the dating is for these fossils?
I don't know specific dating methods that they did use. I just read that they, I'm pretty sure that the latest technology with fossil dating and everything, it's pretty accurate.
So was the impact effect simultaneous, or was it a gradual effect on the global scale?
On a global scale, I'd say over time it affected, but like in a close proximity, everything got wiped out in a short time.
That's about it.
Next to present is Miss Megan Fleming, who is speaking on geologic events supporting how volcanism didn't end the Ordovician. Here's footage of Miss Fleming's questioning period in which her overall argument can be referenced as an opposition to Mr. Sherrill's supporting volcanism for the same extinction, the ordovician. Mr. Sherrill is to be interviewed after the presentations conclude, and the questioning periods for both can be used as context for the interview.
Think about that.
So my research for the ordovician extinction mostly focused on the lack of evidence supporting a volcanic trigger rather than an impact support for the extinction.
But if we have nothing to know that there was an impact, but we know there was volcanism, then would volcanism have just been a larger factor?
Sure, volcanism might have been a larger factor, but it still wasn't the triggering factor for this extinction, so it wasn't really an important factor, I guess, in this extinction.
Could you go back to your prior graph? So dike right there is the volcano reciting, correct?
Correct.
Do you have evidence for an impact prior to this, or do you have any reasoning for the dip in both of the center deltas?
So this would have been from the second glaciation, or I'm not actually 100% sure, but I can assume that it might have been from the second glaciation, or post-glaciation, where the surface, where the glaciers melted.
Can you go to your first graph, please? How do you explain that the mercury levels was lined up with the extinction?
The mercury levels?
Yeah.
Do I have mercury levels?
I thought you had mercury on there. I'm pretty sure you did. Oh, she didn't? I thought I saw that. Oh, okay.
No further questions.
For the ordovician siberian extinction, no concentration of iridium has been identified near the extinction that would suggest a meteor impact like the one identified at the end of the Cretaceous period. How would you explain this?
Just that basically, I don't think impact had a significant effect on this, but also volcanism had an equally insignificant effect, and rather this was caused by the what I have right here, this slide right here, the thermal circulation.
So you claim that volcanism was not the cause, or not a major cause, of the end ordovician extinction. However, there is a feasible theory about gamma rays causing the extinction. With your evidence, can you disprove this?
So I really did not do any research into the gamma ray theory, so I don't know enough about that to know what I would need to say to disprove it. But yeah.
Okay. Could have volcanism happen without impacts?
Sorry? I didn't hear what you said. Can you...
So volcanism was the triggering thing, right? Or no, impact was the triggering thing, right?
For this, no,
Yeah.
I'm saying that impact did have an effect, but volcanism didn't have an effect. Like none of them were really present in this.
So do you know what caused the extinction?
Yeah, it was like the transition between I have this right here, like the increase in the thermohaline circulation, which caused the increase in
That is time.
After a long weekend, everyone has reconvened at the NSF conference on the third and final day of the debate. All research presentations have concluded, and today the committee will release their deciding statement on which group will receive the $500,000 grant to continue their research on mass extinctions.
Before we begin, we would like to thank each and every one of you, principal investigators, journalists, research scientists, and Mr. Walker himself, for your intensive research and hard work, and for respecting the speakers during their presentations. We especially want to commend the PIs on your opening statements, as we appreciated the puns made by the impact side and the cold hard facts used by the volcanism side. As for research scientists, thank you for providing credible and thorough answers to our questions. We will now go through each extinction and explain the reasoning for our decision. First, the ordovician. We thought Mr. Sherrill and Ms. Holland did a wonderful job in providing both general info about the extinction and more specific details about sulfur, glacial expansion, and cooling. Ms. Fleming did a quality job of disputing these, but there wasn't enough evidence for the effect of an impact on the end ordovician extinction. What we gathered was that an impact could have caused the same effects as a volcanism, and not that it did. For this reason, the ordovician goes to volcanism.
Secondly, the Permian. Tam Rai was the first research scientist to present and provided good evidence for volcanism. It shall further explain the evidence and effects of Siberian volcanism, and the big infographic helped. We gathered that the extinction happened relatively gradually, which indicates volcanism. Additionally, the creator attributed to the end-permian extinction was not found to have high amounts of iridium, a fact that cannot be disputed upon further questioning. Although Honolulu did an excellent job of introducing fullerenes, we did not really see their importance. Journey did well in helping us understand more about impact's importance during this extinction, however. Although it was claimed that the impact caused the volcanism, upon further questioning, it was said that the volcanism could have happened without the impact, and that the volcanism was the factor that caused the effects. So the Permian goes to volcanism.
Third, the Triassic. The volcanism evidence for the effects of the camp volcanic events, and evidence such as the strontium curve that occurred, was convincing evidence, but the claystone layer provided by the impact side exempted a causal relationship between volcanism and the extinction, and therefore the Triassic goes to impact.
Yeah!
Fourth, the Cretaceous. Although the Chicxulub impact was proved by Hamza, it was also represented that the impact happened after the extinction started. There was also iridium found at the crater, which further supports impact. Avena presented the Deccan traps, which proved volcanism, but it didn't dispute iridium evidence. The Cretaceous goes to impact.
Okay, so the final, the Devonian. So I thought that the presentations for both of these were exceptionally good, and that each side did a great job disputing why their side was most important. The evidence of the Delta C13 and the effects of the Siberian and Valu traps was very convincing, as well as the glassy spherules. Overall, due to the convincing argument and good graphics, Devonian goes to volcanism.
So this has had everything to do with geobiology, but you might be wondering what this has to do with the now. A sixth extinction is on its way, and humans are the cause. From carbon emissions to climate change, we are letting history repeat itself. What do you see in your future?